This is A Course in Geometry, Plain and Solid, written by Weeks and Adkins. These two guys were math instructors at Phillips Exeter Academy in sort of the mid 20th century. I'm here to tell you this book is traditional. And by that I mean difficult. This book is not here to make friends. Actually, it's kind of what you would expect in a book of this time. It's got exercises that are sort of split into section A for your average prep school student and section B for your ambitious prep school student. Occasionally they'll give you one of these, of interest to you, a challenging problem. Well, and there's actually a little secret about super challenging problems in textbooks. Teachers tend to skip them, and students are glad that we do. But today, I'm not going to skip this problem. I want to take it and turn it into something modern, something with animation, manipulation, full of data. Because I believe that if you really need new problems, you don't necessarily need new materials. Maybe you need old materials. So let's have a look at it, and I'll show you what I mean. It says that triangle ABC is equilateral. X is on AB, and AX to XB is 1 to 2. So this segment is twice as big as that segment. Y is on BC, and BY to YC is 1 to 2. So this segment is twice as big as that segment. Same thing on the third side. Z is on CA, and CZ to ZA is 1 to 2. So this segment is twice as big as that segment. It says that these segments intersect at PQR, sort of forming a smaller interior triangle. And we need to prove that the area of PQR is 1/7 the area of ABC. So there are two quantities of interest: the ratio of how the sides are split up, and we have the ratio of the areas of the two triangles, the smaller interior triangle to the larger outside triangle. Now what's surprising to me is that there's a 1/7 in here. In geometry, we do a lot of, equal to, we do a lot of this is half of, maybe even a third of. Sometimes, I don't even mind if you throw a square root of 2 in there once in a while. But 1/7, no, it's just not done. I want you to notice that I am in Geogebra 5 Classic because I'm going to be gathering data, and I want the data saved to the Geogebra spreadsheet, and I find that easiest to do in version 5. So here's how I drew the problem from the book. I've already sketched it out. I'm just going to show you how I sketched it out. I started with a point C and then drew a point B sort of far away from it. I connected those two to make the base of my equilateral triangle. To make sure that I had an equilateral triangle, I drew these two circles and added a point at their intersection, and then I finished drawing in the triangle. Don't need the circles anymore. Okay, to measure the area, I have to recognize that that is a polygon. Now I'm going to put a point Z on side AC. This point Z is going to be manipulable so that I can change that ratio 1 to 2. And that way I can see if there's a relationship between the ratio of the segments and the ratio of the areas. I need to make sure that the points on the other two sides, the point on AB and the point on BC, that they're the same distance away as Z is from C. So I'm going to draw a couple of circles that have that radius in them. I can put points at their intersection, turn off these circles, and you can see what I have now. I sort of have 3 equidistant points in the triangle. I can then draw in these inside points and show points at their intersection. Again, I have to tell GeoGebra that I have a polygon in the center that I want to measure. And now you can see I'm going to measure the distances that the problem had. I'm going to measure the distance from Z to A, the distance from Z to C, and I'm going to calculate their ratio. That's what I call side ratio. I'm also going to look at the area of PQR, the internal triangle, and the area of ABC, the outside triangle, and I'm going to calculate that. Both of these quantities I'm going to record to the spreadsheet, which I have over here. Since I made Z movable, I can now move point Z to adjust that ratio and gather some data.
Let's move z down to here and move it all the way up towards there. And you can see I've now got a ton of data. Okay, now that I've got the data in GeoGebra, I want to look at that data. So I'm going to copy this data, move over to Desmos and paste it into Desmos. Wow, have we got an interesting curve. Remember what this represents. The x is the ratio of the segments. I changed the size of that point z so that the ratio of those two segments changes, and we're looking at the ratio of the areas of the small triangle to the big triangle. Okay, well, look at this curve. What do we see? As x gets really large, it looks like we've got sort of asymptotic behavior. If I put a curve at y equals 1, you can sort of see that we are approaching 1 as we move along. So what does that tell us? Well, we've got an asymptote. We're dealing with ratios of segments, ratios of areas. I think we've got a rational function here. And if I sort of zoom in to closer to the origin, I can see that this ratio has a root at x equal 1. I need a rational function with a root at 1. So what if I do f of x equals x minus 1 over x? So it's got the root at x equal 1, and it's got an asymptote that appears to be approaching y equals 1, but it doesn't look anything like my curve. And I think that's because what we've actually got here, this curve comes down to its root, it just touches the axis and then moves away. In my opinion, that's telling me that this is a multiple root, at least a double root. So if I'm going to have x minus 1 to give me that root, that x minus 1 needs to be squared so that it just touches the axis. I need a rational function. If I put just an x in here, that's not right. We don't have an asymptote approaching y equals 1 because, as we know, if the asymptote is going to approach y equals 1 as x gets larger and larger, the coefficient of the largest power in the numerator and the largest power in the denominator have to be the same. In the numerator, I've got x squared with no coefficient. If I put an x squared in the denominator, I'm a little closer. I do have an asymptote that's approaching y equals 1 as we go out here. It is touching the root that I want it to touch, but something weird is happening at x equals 0. We can see in the rational function we've got here, if I plug in a 0, this function is going to blow up. We're going to at least have a hole in this function. We don't want a hole in this function. We want this function to be equal to 1 at x equals 0. That corresponds to the point where the ratio of the segments is literally 0. So the ratio of the area of the small to the large triangle is going to be 1. All right, I need it to go through the point 0, 1. How am I going to do that? Well, I'm looking at my numerator here. At the point x equals 0, my numerator has the value 1. If I plug in 0, 0 minus 1 squared, that's 1. So I need the denominator at x equals 0 to also be 1. The easiest way to do that is to write plus 1 in the bottom. And look, we are a lot closer. I'm going through the point I want up here, I'm going through the point I want down here, and my asymptote, this curve is approaching 1 as we get x larger and larger, but it's not really approaching at the same rate. You've got to do something. You know, your idea may be to put a coefficient on x, and let's sort of slide that around to try and approach this axis. But as we already know, that's not going to work. The coefficient of the x squared in the numerator, coefficient of the x squared in the denominator have to be the same. It's a 1 up top, so I think it's going to have to be a 1 down in the bottom also. All right, what other options do we have? Well, the numerator, if I actually squared out x minus 1 squared, I would get x squared minus 2x minus 1. There's an x term in there. So maybe if I try putting an x term in the denominator, we will get closer. So let's do x squared plus x plus 1. And look, we have hit it spot on. This is pretty much a perfect fit. If I move out, you can see that it hits all of the data points of our plot. So if I plug in the ratio of the segments, in the original problem that was 1 to 2, then I get out the ratio of areas. In the original problem, that was 1 to 7. So if I come down here and ask what is f of 1/2, what's that mean? That means when the ratio of the segments is 1/2, what is the ratio of the areas? And look, it's exactly 1/7, which is what the original problem wanted us to show. So instead of looking at 1 to 2, what if I look at 2 to 1? Well, I get the same 1/7 out. What does that tell us? That tells us that back in our picture, that having a point up here at the ratio of 1 to 2 and having it down here at the ratio of 1 to 2 produces the same ratio of areas. That is, there's a similarity here. We can do the same for f of 3. That turns out to be 4/13, just like the value at 1/3, 4/13. So our rational function is sort of showing us the symmetry that we know exists in the triangle.
This whole project came from a single problem in a forgotten 1961 geometry book. There are hundreds of opportunities like this for us to take advantage of. All we have to do is look around and have a little curiosity. For example, here, another geometry book, this one by Weeks and Downs. It's kind of the real Mac Daddy of new math proof-based geometry books. And inside of here, guess what they've got? Honors problems. Here's one that uses squares instead of triangles. I mean, what we've done today with that graph, I would say, is better than a proof. I mean, at this point, nobody even cares to see the proof of the original problem, right? Right? All right, next video.